how we approach projectile motion. We'll have a look at that. Okay, so there's our x and y axes, which we'll just conveniently put down. And we would fire our projectile, whatever it happens to be, at some angle to the horizontal, and obviously we'll have a velocity. But then once that projectile has left our hand or cannon or whatever it is that's firing it, the only thing acting upon it at that point then is gravity. It's the only thing. Well, we're assuming no wind resistance and things like that, of course. And as we just saw in that little video, the path of the particle would describe a parabola. And you notice even that one, because of course the one in the video did have air resistance, but even that, still you could see the parabolic shape. It didn't have that significant effect on it. Obviously if it was a strong wind, it quite possibly could. Just an interesting fact there. So maximum range will always occur when you fire at an angle of 45 degrees. So what do we know about this system, this projectile that we're going to be looking at? So obviously there are some initial conditions, but I say I want to break it up into what's happening horizontally, what's happening vertically. So when time equals 0, so I can just draw up a triangle. There's my velocity, and whenever we do it, we deal it with the velocity. So our vectors, if you want to call them vectors, we'll do it with velocities. So I'm using the dot notation, which is Newton's notation for mechanics. We tend to use that when we're looking at motion problems. So I can resolve, well, okay, I know the hypotenuse because I know the resultant, if you like, of velocity, but it's made up of a horizontal velocity and a vertical velocity. We could put those things together to make the hypotenuse. That's just a little bit of trig, gets it easily for me. The horizontal velocity will be v cos theta, which means it's constant. Okay. And y dot theta v sine theta, that one will not be constant. Now how do I know that? It all comes down to what I said, the forces. The only force acting on this problem is the force due to gravity, which is purely a vertical force. So horizontally, it just travels at a nice constant velocity. Also, now, well, it depends where you want to set the origin. I mean, quite often we just set the origin of where we're starting the problem at. Sometimes it's convenient, say you're throwing from the top of a cliff or something like that, you might set the y value to be however high you're throwing from or something. Unless they force your hand in the problem, that's up to you. So it's usually easy to make the origin the starting point. But as I say, we start from forces. Well, technically in 3 unit we don't say forces, we start with acceleration. So, but when we do the extension 2 problems, we actually start with forces rather than accelerations. But it's not a big deal. I mean, it's just the difference, as you should know, between forces and acceleration is simply that force is mass times acceleration. So as I said, horizontally, as far as forces are going, there's nothing happening. So it's equal to 0. There's no acceleration. Vertically, we have g, and I'm defining downwards to be negative. Kind of makes sense. So it'll be negative g, because it's acting in the negative direction. Now really, from here, it's like our tuner problems that we saw earlier, but we're just doing 2 sets of problems. One for the vertical motion, one for the horizontal motion. So I integrate, if you like, so I'll get a constant over there. I'll get also a constant, but I'll have minus gt. Sub in the initial conditions, and I get, there it is, it's a constant v cos theta horizontally, whereas in the vertical direction I get minus gt plus v sine theta. And integrate again, we'll come up with some displacement equations. And initial conditions, we conveniently make 0, 0, so those constants are 0 and 0. And we get a displacement equation horizontally and one vertically. Now with those underlying equations, mind you, we don't really use the acceleration ones again. They're the ones we just use to create the other ones, but with those other ones, we should be able to solve any problem. Of course, we're dealing with a parabola. Basically, what we've got there are parametric coordinates of a parabola. So it's that whole topic we did last year on parametrics with a parabola comes back into play. It's an alternative way of solving projectile motion questions. You could think of it like a parametric parabola. So t was equal to v cos x on v cos theta. If I wanted to work out the equation of the parabola, like we did with parametrics, eliminate the parameter. Get rid of the t. Sub that in, and we can see it is a quadratic. Tidy it up a bit. Oh yeah, let's change the sec squared into a 1 plus tan squared, did I? Yeah. What the heck? Whoops. So there we go. But we can recognise that to be a quadratic. So that's proving, yes, it does turn out to be a parabola. Okay, common questions they like to ask. Things like, oh well, when does the particle hit the ground? And so you just ask logical questions. Well, it's going to hit the ground when vertically the displacement is 0. If that's where I've set the ground to be. If I'm at the top of the cliff and I've made the top of the cliff 0, then the ground might be negative, whatever the height of the cliff is. Hey, you solve that problem. What's the range of the particle? How far did we throw it? Well, in order to answer that question, I'm going to need to know when it hits the ground. So I'll solve y equals 0, and then I'll substitute that into the horizontal displacement. But of course, if you think of the parabola, if you've got the actual equation of the parabola, you could say, hang on, the roots of the quadratic. Because one root's going to be where I started from, assuming I'm standing on level ground, then the other time it hits would be the other root of the quadratic. So I could use that. What's the greatest height of the particle? We go, so what happens at the greatest height? That's when it stops going up and starts coming down. So vertically, that's when its velocity would be 0. Okay, so that's what we've got to find. When is vertical velocity equal to 0? Then I'll substitute it into the vertical displacement, and that'll tell me how high it went. It would be the vertex of the parabola if we had the equation of the parabola. Well, it'd be the y value of the vertex, of course, minus the discriminant on 4a. What angle does the particle make with the ground? And this is where we play with the vectors to get the angle. Whenever we play with the vectors, it's the velocities that we play with. So we need to find when it hits the ground, first of all. Then we'll find the vertical velocity. The horizontal velocity is, of course, constant. And then we say, okay, that angle would be a bit of trig. The tan of the angle would be the vertical velocity over the horizontal velocity. Now, some people argue that the angle that it hits the ground would be the obtuse angle, not the acute angle, but it's trivial, really. I mean, it's still the same angle when it hits the ground. In fact, it doesn't have to be the question where it hits the ground. It could be at any time. So at any time, you would just draw up a little triangle for that particular moment in time, and you can work out the angle that it's at, and so on. If you had the parabola, you're basically talking about the tangent. What angle is the tangent going? So you find the slope of the tangent, and we know slope equals tan theta. And that would get you the angle at that point. So in summary, any particle undergoing projectile motion simply obeys that. That's really all we know. They're the forces acting on it, or the accelerations. And then we can combine it with initial conditions that we know about the problem. And from there we should be able to solve any problem. So let's do it. Throw a ball, initial velocity 25 meters per second, angle conveniently I've written as inverse tan of 3 on 4 rather than actual angle. Work out, so greatest height. Okay, I'll work out my initial conditions. I've drawn up a triangle. So x dot would be v cos theta. So sometimes you'll be playing with an actual number. Sometimes you might be leaving it as just v cos theta. They might not tell you the actual angle. They might not tell you. You might just say, oh, travels with the velocity v at an angle theta. So in this case, we've got an actual number, 20 meters per second, vertically 15 meters per second. Okay. Now, I'm just going to go through that whole process again. I've set gravity to be 10 rather than 9.8. You'll see them do that a lot in the problems just to basically make the maths easier. But be careful to make sure you know what they're asking your gravity to be. So I'll integrate, essentially the same as what I just did, but now it's got some numbers to play with. So there's an expression for velocities. Now we'll do displacements. You'll notice I've done these by finding the constant. Of course, you could do them as a definite integral. So if I did them as a definite integral, the only difference would be like so. So I don't actually find the constant. The constant comes in the calculation. And there's x dot. And y dot, same answers of course. And then displacements. So however you prefer to do them, definite integral or by finding the constants. But we have our equations. We should now be able to solve our problems. We know the greatest height occurs. Explain what you're doing. Don't just write down a whole heap of numbers and equations and come up with an answer and go, whee, here it is. Explain what you're doing, because heaven forbid, should you make a calculation error or something like that, at least they can read through your logic and they go, okay, well they do understand what you're talking about, and you never know, that might be good enough to get a mark. So t equals 3 on 2 for this one. So let's substitute that into y, and we get 45 on 4. I always like to answer the problem. So greatest height. In this case, I will write it as a mixed numeral. It just seems to make more sense. When you talk about how high is it? Oh, well, it's 11 1/4. You don't tend to say, oh, it's 45 on 4. That's how high it is. Again, it doesn't really matter. Range. Okay, straight away, I know the time of the flight for this one is 3 seconds. Because I know I'm dealing with a parabola. I released it from the ground. It's hitting the ground. It's got to be symmetric. So therefore, I don't have to do any more calculations other than to say, I know my time of flight's doubled from when I found the maximum height. So those little things about using the shape of the parabola can save some time in calculation. Time of flight's 3 seconds for this one. And so we'll hit the ground 60 metres away. So there's our range. Velocity and direction after half a second. All right, well, we've got to find our velocities. We know horizontal is constant, so that's 20. Vertically is positive 10. Now that makes sense because we said that it took, 1.5 seconds to reach the greatest height. So after half a second, it must still be going up. So its vertical velocity is positive. So vertical one's positive, I'm going up. Horizontal 20, there's my triangle. So 10 root 5 is the hypotenuse. There's my velocity. And a bit of trig, the angle I get about 26 degrees 34. What is the Cartesian equation of the path? In other words, get rid of the parameter. Okay, well t is x on 20, and we get y is minus x squared on 80 plus 3/4 of x. So all right, now that I've just come up with that Cartesian equation, let's solve that same problem, but using quadratic theory. So we said greatest height. Well, I know greatest height is the y value of the vertex. So I can go minus the discriminant on 4a. The discriminant of that quadratic is 9 on 16. So minus the discriminant on 4a, 45 on 4. There's the greatest height. Part B said the range. Well, I can easily find the roots of this by factorising my quadratic. Obviously one answer is 0, but the other answer would be 60. So I know the range is 60 metres. Velocity and direction of the ball after half a second. Well, this is playing with the tangent to the parabola. So the derivative, so when t equals half and x equals 10, I need to do that because my derivative is in terms of x, not in terms of t. So I still need to work out what is that horizontal displacement. Sub that in, I get y dx is a half. Not a coincidence, because you remember before we got that equation that tan theta was a half. Obviously we get the same. And so we found the direction. To find the velocity, well, v could be written as x on t cos theta. I've got x, I've got t. So I should be able to sub in. Oh, rather than subbing in 26 degrees 34, I've just redrawn the triangle there to get exact values to sub in, and I get the 10 root 5. If I use the 26 degrees 34, obviously I wouldn't have got the 10 root 5, I would have gotten an approximation. So it gives you an alternative way of solving those problems. So 3G, 3H, a mixture of projectile motion questions now.